We're here to learn about the Drake equation, but I have an ulterior motive, and that is to talk about what I deem the reduction of scientific ignorance. So I've used this chart many times in talks over the years. By the way, I gave this talk last time about 8 years ago. This will be the third time I've given this. So those of you who have seen this before, feel free to nod off. This graph shows the reduction of scientific ignorance. So the way I characterize it is that red line, that red curve, is called an asymptotic curve. It's a curve that gets closer and closer to a value, but never quite reaches it. And this is the way that I view scientific progress of any given sort. Given a topic, whether it's biology or chemistry or astrophysics, we're somewhere along this red line. You know, if we're way down there on the, what is that for you, the left-hand edge, then we don't know a lot. Our model of reality, I like to distinguish between scientific models and scientific facts versus natural facts. That nature is as nature is, and scientists' job is to try and understand it and potentially model it in such a way that we can make predictions and statements about it. So we can be far to the left on this asymptotic curve, meaning that whatever particular natural system we're talking about, our model is poor. We don't really know enough to model it correctly. And then as time progresses, our ignorance about that particular natural system decreases. And the goal is to approach perfection. I know that's my goal. I hope that's yours as well. And actually a more perfect description of reality. So that's the way I like to view much of scientific progress. It's why we can say things like, oh, those scientists have changed their mind. Well, sometimes that happens. And that's because they're taking a further step along this curve of reduction of our ignorance and a more perfect understanding of the natural world in which we find ourselves embedded. So we're going to talk about this concept as it relates to the Drake equation. So science is, as I said, a process of discovery resulting in an asymptotic approach to a perfect model of reality, right? Well, one of the things we can presume is that the Earth is flat, right? I mean, for many things, for many contexts in which we find ourselves, a flat Earth is a perfectly reasonable approximation of reality. If you're building a house foundation, for example, then assuming that the Earth is flat is more effective than assuming that it's curved. However, if you're building a very long straight road, sometimes if you're going north-south on a long road, you'll notice that sometimes you have to jog over a little bit. And that's because we live on a round planet. And you have to take into account of that. Otherwise, you draw a straight line and it goes off the curvature of the Earth and you can't drive into space. So, yet, right. So at larger scales, even though we can approximate the Earth as being a flat surface, at larger scales, such as Switzerland, you find that Earth is better approximated by bumpy terrain. And so you deviate from flatness. And then on the very largest scale, right, you get up in an airplane, and even from a height of 20,000 feet or 25,000 feet that jumbo jets fly at, the Earth still looks pretty flat. Right, the horizon is not noticeably curved. But if you get far enough up in space, then obviously you see that we're on a spherical planet. And the smoothness of the planet in terms of being able to be represented by a sphere, the Earth is smoother than a billiard ball on a pool table. In terms of the percentage height of the little bumps deviating from perfect smoothness and roundness. Right, so Drake's original estimates for some of the terms in his equation. Let's talk about some of those. The rate of star formation in our galaxy, assume that about 1 star per year. The number of stars that have planets, he thought maybe it was to 50%. The next one is how many planets per star? Maybe 1 to 5 planets per star. How many of these planets around a star will develop life? He was very optimistic and said 100%. Every planet, you're laughing at him, right? I mean, this was 60 years ago, and we didn't know as much about biology and astrophysics, but it is fairly laughable, right, to presume that every rocky planet around a star will develop life. And how many of these planets that develop life will develop intelligent life? Well, he believed it was almost a certainty, if not 100% certain. And then the fraction of intelligent species that progress technologically to the point where they can communicate via radio or laser, or, hurling pieces of matter at each other through space or whatever. 10% to 20% of which will be able to communicate. And then what's the average lifetime of an intelligent communicating species? He estimated somewhere between 1,000 and 100 million years. So that'd be a long time. Human species, Homo sapiens, have only been around for about 500,000 years, and so that would be. Isn't that right, Mike? You're the biology guy, I think, generally. All right. So, oh look, I've got nice illuminations on those. Yeah, who needs them? So we're 60 years further along on our curve of reducing our ignorance about many of the factors that go into making intelligent or plausible statements regarding some of these terms. The rate of star formation. So we've had several space telescopes up there. One of the things about baby stars is that they're typically encased in a cloud of gas and dust particles, and so they're very difficult to see, especially at optical wavelengths. So this is where our infrared telescopes have really helped. Some of you may be familiar with an infrared telescope named, what's that big one up there now? Webb, James Webb, yeah. So we look at places like this. This is an image of the Orion Nebula, and the Orion Nebula is literally a hotbed for star formation. And you've got your baby stars are in there. I've got all kinds of pictures of baby stars I've shown in other Science Sunday presentations, but lots of stars are being born there. And so the rate of star formation in our galaxy is estimated currently to be between 1 to 3 new stars per year in our galaxy. And that's pretty impressive. So Drake wasn't too far off with that one. Am I thumping too much? Yeah. All right, thank you. All right. So next is what's the fraction of stars that likely have planets? And remember I said there'd be a quiz. Frank Drake back in the 60s said 100% that every star is likely to have planets. And currently, we know up until the 1990s, we knew of one star that had planets. And so this is a bold statement on the part of Frank. And it was an extrapolation from the fact of something called the Copernican principle, that there's nothing special about our place in the universe, there's nothing special about our star, etc. And so applying the Copernican principle to say there's nothing magical about the Earth, nothing magical about our star, etc., he said, well, then it seems plausible to me that every star will have planets. And if you look at the number of known exoplanets, the planets outside of our solar system that have been known, I think 1991, the first one was discovered by looking at a planetary, probably a remnant, that circled around a neutron star and affected the signal that we get from that neutron star or pulsar. And that was back in the 90s. And then since then, there's just been an avalanche of new planets discovered. First time I gave this presentation thereabouts was I don't know, 12 years ago, something like that, or 11 years ago or more. And in 2013, the number of known exoplanets just skyrocketed. And that was because of the Kepler Space Telescope that was specifically designed to look for signatures of planets orbiting stars. And so the current estimate is that there are essentially as many planets in our galaxy as there are stars. So Frank Drake was generally correct with his estimate. Once again, um, just extrapolating from the Copernican principle that there's nothing special about our star and our place in the universe. And since then, we've had the James Webb Space Telescope, we've had the Hubble Telescope, we've had the Keck Observatory. There's some giant additional telescopes that are being built elsewhere in the world. And one of the primary astronomical targets for a lot of these telescopes is looking for planets around other stars, and then ideally uh, discerning some of the properties of these other planets. How big are they? Um, do they have thick atmospheres or thin atmospheres? Do they have oxygen in their atmosphere? Which would be very remarkable. But in any case, we remain at having an estimate down here at the bottom. I show the handy equation. So the fraction of stars with planets is still estimated to be about 1. This is a picture of some baby planets around um, a relatively newborn star. I believe this is Fomalhaut B is the name of the planet. Fomalhaut is the name of the star. And this particular planet, you can see the arrow pointing at it there. So they've tracked the orbit of this little blob over time. This is where it was in 2004, and this is where it is in 2012. And so by looking at the characteristics of its orbit, they have estimated that it's about 2 times the mass of Jupiter, so gigantic planet. And it's relatively young. As I said, this is a just out of infancy stage in terms of stellar evolution. So this is a very young star that's about 450 million years old, about a little bit sooner in time than the Cambrian explosion. So when multicellular life was crawling around in Earth's oceans and swimming in Earth's oceans, this star was being born. You can compare this Fomalhaut star and its associated planets with the solar system. And one of the things about naming planets in other stars is that the star is A. So Fomalhaut A is the star, and then Fomalhaut B would be the first planet discovered in the Fomalhaut system, etc. So it's called Fomalhaut B, even though it's the first planet discovered. And here's an image of another 3 or 4 planets around a different star. The center of the image looks like kind of optical garbage. You know, they use special techniques to try and blot out the light of the central star. And then all we see off of any given planet is just the reflected light. So you really have to do something clever to try and get rid of the light of the star. Otherwise, it overwhelms the image. But it's a star with many planets. One of the problems with this particular star, if we start imagining what it would be like to live on one of those planets, is that it's a highly variable star. Our sun is slightly variable. The 11-year solar cycle and 22 years to get back to where it started. If you think of a sine wave, it gets back a couple times. So crosses the axis in terms of brightness a couple times during a whole period, and the period is 22 years, and it's slightly variable. But a really significantly variable star might dim or brighten by 50% or 20%. And imagine trying to live on a planet where we didn't just have to take into account the seasons, but also throughout a period of 100 years or 50 years or 10 years, whatever the period of variability of the star is, the climate would change dramatically. And it's hard to imagine life evolving perhaps beyond a microbial stage, even if it reaches microbial stage around such a variable star. There's another image of a star with its planet. The central star is being blocked out in this image. And here's what we know about planet sizes. So you see Jupiter on there and you see Earth. And then these are some of the planets discovered by the Kepler spacecraft and how they compare to the sizes of planets in our own solar system. So you see a lot of planets, relatively speaking, that are bigger than Jupiter. Well, one of the reasons for that is because they're easier to find. If you got a big, massive planet, it shows up in your data much more vividly than a puny little planet the size of Earth. So we know about a lot of giant Jupiter-sized and above planets. And then the number of known planets by Jupiter equivalent mass. So the ones that are lighter than Jupiter, or the first bar here, and there's 100 or so known planets of that size, and then a bunch of planets that are the size of Jupiter or larger. And this is data again from about 2018. I've got another slide in here that has some more updated data. Right. And one of the other things about our solar system is that the giant planets, Jupiter and Saturn, are relatively far removed from the orbit of the inner planets. So Mercury, Mars, Venus, Earth. If you had a Jupiter-sized planet that was close to the sun, perhaps even closer than the orbit of Mercury in our solar system, it's what's called a hot Jupiter. And there have been many hot Jupiters that have been found out in space. So one of the speculations about our solar system is that Jupiter likely formed closer to the sun, but then moved out over time. And it's a good thing. So Jupiter plays a pivotal role in keeping our solar system clement. It catches comets, the Shoemaker-Levy comet that crashed into Jupiter a couple decades ago. And I think there was one recently, a smaller comet or asteroid, I don't remember which, that impacted Jupiter over the past couple of years. So Jupiter does a pretty good job of keeping it's got enough mass that it essentially attracts a lot of the debris that would otherwise be more prevalent in the inner solar system and would be more likely to hit Earth. So having a Jupiter far away is good. And then this is again from about 2018. At that point, there were 786 known planets, and this is a way of representing them to scale. Now there are many more than that. I'll tell you the number here in a minute. I think this is by Randall Munroe, a science communicator who is famous for saying, "What if? What if you had a Death Star kind of thing, and how much material would it take?" And I've talked about that. That was one of my first Science Sunday talks. So as of June 2013. And this is today, essentially, the number of planets since 2013. So we started off with about 700 or 800 known planets, and now we're up above 5,000. So I mean, mind-boggling. What can you say? 5,000 known planets. We are certain that these planets exist beyond our solar system. And that's just a fraction of the stars. If you were to look at the number of stars that are close enough to us that we can do the kinds of observations necessary to detect planets, you'll note that it's only a bubble that's about, I don't know, 100 light years or 200 light years or so. And so just a tremendous number of planets relatively close to us. And this is the method. The color is the method of discovery. So a transit of a planet, that's when a planet moves in front between the star and our telescope that's looking at the star. So it it tends to dim the light of the star by to a human eye, it would be an imperceptible amount, but our instruments are able to detect it. And so that transit that happens when a planet goes in front of the star dims the starlight, and we can measure that and estimate the size of the planet. And from the size, often we can extrapolate something plausible about its mass. Now, one of the problems with that method is if you were, for example, trying to spot the transit of the Earth in front of our sun, you'd have to be very lucky because it takes 365 days thereabouts to go around our star. And so unless you happen to catch the Earth from your point of view transiting the sun in a matter of a particular day of the year, then you wouldn't find it. So the transit method is good for planets that are close in near their star because they orbit more quickly. Mercury orbits much more quickly than the Earth. Jupiter orbits very slowly, etc. So the closer the planet is to its central star, the more frequently it transits its star, and the higher the probability that it will be discovered.
And it has to be on the same plane.
Right. Yeah, you have to be at the correct angle, right? So between the telescope, the planet, and the star. So if the star, if this is a star, it's conveniently yellow, and the planet is orbiting this way, and you're looking at it, you're never going to see a transit, right? But if it orbits this way, you very well may. Another method is radial velocity. So by looking carefully at a star and its relative position in space, sometimes, I'm not going to move the microphone because it's very sensitive, but stars jiggle a little bit, and you can measure that jiggling to try and, yeah, you had to, wait for the microphone because we're on a video, so.
Test, 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 test.
Okay. Yeah, if it's measuring radial velocity, it's probably using red and blue shift. So
Yeah.
what that is the Doppler effect of a car going by and it sounds higher pitch coming and sounds lower pitch going, right? Light does that too. So if the source of light is moving towards you, the wavelengths get shorter, which means they get bluer. And if they're moving away, wavelengths get longer, and so they get redder. And that slight shift in wavelength is actually, we can measure very precisely.
Right.
And so that's probably what they're measuring there to see it moving towards and away.
Exactly. Yep, exactly correct. So that's the radial velocity. They can detect the motion of the star by, again, looking at the color of light emitted by the star. And then micro lensing is another, where you've got a massive object between the star and its potential planets and yourself. So it's essentially Einstein's gravitational lensing allows us to zoom in, as it were, on stars that are more distant. And then there are other methods that tend to be more. We find them by happenstance. So, like the timing of the pulses from the neutron star indicated that there was a mass orbiting that neutron star. That was the first exoplanet that was ever discovered, for example. So, some few other methods, and then direct observation. Right, we saw a couple of images around Fomalhaut and whatnot of actual images of other planets, but it's extremely rare that we get that opportunity. The other thing that's possible is habitable moons. I think Mike talked about that a little bit. The possibility of life on some of the moons in the outer solar system. And if you've got a giant planet and a moon orbiting it within the habitable zone of its star, then perhaps that moon could develop life and evolve life from there. And so this is just an example of sort of a speculation about a habitable moon, and it might look something like this, right? Where you've got in the background, in the far distance, you've got your giant planet that's kind of like Jupiter. But if you've got a moon that may be something approaching Earth-sized, it could retain an oxygenated atmosphere. So this is highly plausible that there could be habitable moons in the universe. And then One of the because when a planet is close to its star, it is more likely to be detected by our instruments. One of the consequences of that is we've discovered a lot of planets around what are called red dwarf stars. And red dwarf stars are pretty amazing in their own right. Most of the stars in the universe are thought to be red dwarf stars. They are far more numerous than other stars. And in fact, if you look out at our night sky, you can see exactly 0 of them because they're very dim. And so you can't see them with the naked eye. You have to use telescopes to spot them, but they're more numerous than the stars you can see. That's a good thing. Another good thing about red dwarf stars is they are thought to live as radiative bodies for something like 1 trillion years. So that's impressive. Our sun is expected to have a total lifetime of about 8 billion years. And of that, about 5 or 6 billion years of that lifespan find it well behaved enough to make an environment suitable for life. But around a red dwarf, so a red dwarf star would be a good place to move to a planet if we wanted to, outlive our sun, for example. But there's a problem with red dwarf stars. They tend to be very, very active. They misbehave, and they're often ejecting huge solar flares that transfer a tremendous amount of energy to the nearby environs. And in order to be in the habitable zone where you get liquid water, that's the definition of a habitable zone around a star. If you have a planet close enough to this dim star to be where liquid water can exist, it's also close enough to be periodically fried by these frequent and powerful solar flares or star flares. So there's different kinds of planets. We've got super Terrans, which are kind of super Earth, somewhere between the mass of Neptune and Uranus and Earth. So we've got super Earths, we've got super Jupiters. All kinds of different planets have been provably discovered in the galaxy, in our nearby galaxy. So the number of planets and moons that could potentially support life per star system. So we're here on the 3rd term of our equation, and has to be in the habitable zone, so where liquid water exists, stable, relatively calm star. A metal-rich system, I didn't really talk about that, but you have to have carbon, for example, and other heavy elements to make life possible, to make the chemistry possible. And that star has to stay within a hospitable region of its galaxy, right? If it's a star near the core of the galaxy, it's likely to be too unpredictable with chaotic orbits and stellar explosions and maybe a supermassive black hole that you might have to worry about. So being in the habitable zone of a galaxy is also important. And the current estimate for the number of planets per star that could harbor life, so it's in the water zone, etc., is something like 0.5% to 4%. That's not particularly high. I think Frank Drake estimated that this number was 1. So 4% is 0.04, which is a long way from 1. But considering that we have 100 billion or so stars in our galaxy, you multiply a small number by a gigantic number, and you still have a lot of opportunities for life to evolve. All right. The fraction of life-friendly planets that actually develop life. Well, we've got a good data point for that, and that is Earth. So one of the interesting things about Earth is that when looking at fossil evidence for life in chemical signatures and physical fossils in rocks on our planet, scientists have concluded that life developed within a few 100 million years of the Earth coalescing from the gas and dust debris from which our solar system was born. And that gas and dust was enriched by the material ejected from a nearby ancient supernova, one or more ancient supernovas. So we get the heavy elements that I alluded to earlier. And only a few 100 million years after the Earth turned from a ball of lava into a ball that might have had some liquid on the surface, probably not land on the surface yet, but life evolved or developed first in oceans, most likely. And anyway, a few 100 million years. So that tells us that the chemistry that goes from prebiotic chemistry to biological chemistry or organic chemistry, that kind of step can happen relatively soon after a planet is formed. So that gives us confidence that primitive microbes might exist around other planets. However, there are some special circumstances about Earth. Remember, I talked about the Copernican principle? There are some aspects of our planet that likely set it apart from a run-of-the-mill planet with a mass about the same mass as Earth. One of them is that it's believed that we once collided with another planet. Our planet collided with another planet when worlds collide, right? Probably not something you want to be around to witness. But a couple of consequences of that. One is that a lot of the silicates that form the lighter material of our planet, right? The metals sink in towards the core, and the lighter materials come up to the surface. And it's thought that the Earth originally had a silicate crust that was quite a bit thicker than what we see today. Thanks to this planetary collision, a lot of that crust material was ejected off. It melted off and formed a blob, and that blob became the moon. So because the silicate material on our planet was thinned out due to that sloughing off of additional material, it made the crust thin enough that it could undergo plate tectonics. It's the only planet or moon. Well, that's not strictly true. There's some ice flows and whatnot, evidence on other moons. But in terms of moving silicates around on the planet and really churning up the chemistry necessary to create the conditions suitable for life's origination, Earth is really special in that regard. And then also just the fact that we have a moon is important. The moon helps shield us from debris in space. It also gives rise to tidal pools. One of the speculations about the formation of life, so abiogenesis, the formation of living things from non-living chemistry. One of the speculations is that tidal pools were relevant to that. Nobody knows for certain. We didn't have scientific instruments on the early Earths, which is very disappointing to me. But in any case, the tidal pools resulting from the orbit of the moon likely created conditions that were at least hospitable to some kinds of life, if not the origin of life itself. A hot core with a magnetic field, that's something our planet has that's very helpful. I talked about the thin crust, the magnetic field that shields us, and an ocean with dry land. So all of these things are parts of our Earth that help make it hospitable for life and the origin of life. Here's a dramatization of that collision. This happened in our, well, we don't know where on Earth this happened because the plate tectonics has moved things around so much since that collision early in Earth's history that this is still somewhat speculative, and I could go into reasons for that, but we'll skip that in the interest of time. So the terms of the equation, the fraction of life-friendly planets that actually develop life, to be honest with ourselves and consistent with the known science, it's somewhere between 0 and 100%. So I hope you're satisfied with that answer. Yeah, narrows it down quite a bit. But it's, again, we're being honest with ourselves. We don't know. We don't know how many of those aspects of our planet that make it somewhat special. How often do those same aspects occur elsewhere in our galaxy? and how many of those aspects are truly necessary for the origin and evolution of life. So we don't know. And sometimes that's the best we can say in science, and it gives us further reason to explore. And one of the things we're exploring is our own solar system to see if life exists there. I'm sure Mike talked about some of those experiments and some of those missions that are planned for some of the outer moons in the solar system looking for the possibility of life. There was recently some material returned from a meteorite, I think, that had microbes on it, but the microbes, the DNA and whatnot, look like they're Earth microbes. So the question is, was that sample contaminated, or was it a piece of ejecta from Earth? I don't know. I haven't read about much on it, but there are potentially plausible explanations for how Earth-like or Earth analog microbes ended up on a meteorite, and the most simple is that it was contaminated by Earth material. The next is the fraction of life-bearing worlds that develop intelligent life. So there's an argument to be made that certain corvids, crows and whatnot, are intelligent. Not as intelligent as humans, but still remarkably intelligent. I think the neural density of birds is something like 7 times the neural density of mammals. So with a bird brain, you can actually do a lot. And another potentially intelligent creature on Earth is dolphins. One of the problems if you develop intelligence in a creature that lives in the ocean is it's hard to imagine how technology might evolve from there. Right? How are you going to smelt things? Right? How are you going to run foundries? How are you going to create silicon chips in a clean room, etc. If you're evolved and your habitat is underwater? So you may have intelligent species that live in the water, but maybe they're not technological. We'll talk about technology in a minute. And right, climate catastrophes could pose a problem for intelligent life, and the safety in the cosmic neighborhood from asteroid and cometary impacts. Right, we've had several mass extinctions on Earth, and Earth is a pretty hospitable place around a pretty docile star, and yet every 500 million years or so, give or take, we have some kind of mass extinction, often due to either the results of runaway plate tectonics or an astronomical event like a comet or asteroid. Another thing that's important for intelligent life is first you have to develop complex life. So the leap from single-celled bacteria and archaea to eukaryotic life, multicellular life, that leap took billions of years on Earth. For something like 2 billion years or 2.5 billion years, the only life on Earth were bacteria, essentially. And the leap from that to a complex cell with organelles in it, like mitochondria and the nucleus and the Golgi bodies and all that good goopy stuff that goes into complex cells, that seems to have taken a long time, which tells scientists who speculate about these things that it was a very rare event. If life was around for billions of years before this happened, then whatever happened to make that first simple eukaryotic or complex cell, whatever that was, it was an extremely unlikely event, right? What if that never happens in most places? So it is scientists feel fairly confident in making the speculation that most of the life elsewhere in the universe is single-celled life, which would still be pretty remarkable, right? The leap from non-living to living perhaps is a fairly easy jump, but from living single cells to living complex cells, a cellular life, that may be highly uncommon. So again, I give you this confidence range from 0 to 100% for intelligent life evolving on another world. And then the fraction of the worlds with intelligent life that develop technology, like the city of Chicago pictured here, a highly technological instance of a species that has developed amazing capabilities. And we've got to have tool-using bodies. So we have to evolve the capability to manipulate our environment in intricate ways. What about fossil fuels? Could we ever have developed a complex technological civilization without fossil? What if we were still burning trees? What if we were still using windmills, right, to process our food and whatnot? So without fossil fuels, disregarding the associated perils that we've discovered relevant to fossil fuels, but without fossil fuels, without that dense source of energy, could high technology develop? Accessible metals, right? Our thin crust with aluminum and iron and other elements available just from scraping out a tiny depth into the crust of our Earth. Is that likely to happen in other worlds? Consider that only about 25% of civilizations at a given time on planet Earth appear to have aspired to technological advancement. So think about indigenous populations in different parts of the world, perfectly intelligent, perfectly highly adaptable, smart human beings who exploit their environment for survival and ritual and trade and whatnot. But do they develop silicon chips and rockets? Probably not, right? So that entails a certain amount of civilizational aspiration or a social aspect to developing high technology. In the Paleolithic lasted for a couple 100,000, 300,000 years from when our species developed to when we get to the Mesolithic and the latest technological advancements that we made with agriculture and whatnot. For a long time, our Homo sapiens sapiens species existed in a world where leather and wood and stone was perfectly sufficient to provide for a lifestyle for vastly longer than we've had what we would call high technology. And then what about broadcasting, right? One of the ways we want to try to detect intelligent species is from broadcasting. Well, one of the things we're not doing so much anymore is broadcasting. We use point-to-point technologies. We use satellite connections, focused beams of energy and electromagnetism, and then fiber optics, all the fiber optics that are running through the ocean and whatnot. So we've gone, your television, how many of you still watch television from signals broadcast over the air? 2, 3, right? Most of our media comes via fiber connections or copper connections and whatnot. So Earth has kind of gone quiet. And if that trend continues for 100 years or so, maybe anybody looking for radio transmissions from our planet will find virtually nothing. So maybe we'll hide ourselves just accidentally. So again, I give you this range, 0 to 100%. And then the lifespan in years of a technological civilization. So let's say we've had high technology for 300 years, since the beginning of the Industrial Revolution. And you have to consider what's the lifespan. We don't have much data to draw a conclusion from, right? But there are all kinds of perils that we face, both due to our high technology and regardless of our high technology. What is the frequency of unavoidable, natural, or self-inflicted extinction events? We don't know, right? We've got this peril, which we don't talk about much anymore, nuclear war, that would set us back technologically, perhaps to the point where we're living in the Neolithic again, or the Paleolithic. Cometary impacts, right? We've got all kinds of programs. NASA has an ongoing search for near-Earth asteroids and threats to our planet. This is a picture of Ebola, right? We recently went through COVID. What if a more virulent and more deadly disease develops. It probably will at some point. We just don't have a way to estimate the frequency of these things. So looking at the original estimates from Drake and the estimates from today, we see that there's this huge range of possibilities for estimating the likelihood of there being other intelligent, technological, advanced civilizations in our galaxy at the same time that we are also stepping foot into space from our planet in the galaxy. So it's progress, right? Especially for the early terms of the Drake equation. We know more about some of those variables than we did 60 years ago, but many of them remain elusively undetermined and, for the time being, undeterminable. And then we have a closing paradox. If there are other communicative, advanced, intelligent species in our galaxy or in our neighborhood, where are they? Right? And I'm thinking about giving a whole talk related to this, just sort of rolling with this theme. Maybe next time I'll give a talk about the Fermi paradox and the possible solutions to the idea of where is everybody? A question that Enrico Fermi, the folk wisdom has it that Enrico Fermi was in a cafeteria, I believe, it was at Los Alamos during the bomb project, that he said, "Hey, where is everybody?" I'm like, well, we're all here. Well, no, I don't mean you guys. I mean the little green men. So, and then what about interstellar travel? Think about, in order to pick up a signal from just a radio signal from another civilization, you'd need a detector somewhere between the size of the Arecibo disk and the moon, right? Depending on how far away it is, to get a good signal to noise ratio. It becomes implausible if that civilization is further than a particular relatively close by distance. And interstellar travel, right? Well, I mean, picking up radio waves is one thing, but going to visit the little green women and men, not likely. I've given a talk about that in the past too. So, are we alone in the universe? We don't know. And that's, I think that's it. So, anybody have questions or comments to go along with today's theme?
We can't just go to New Jersey and find them there?
Well, maybe. I actually received an email recently from one of our friends who was speculating about the provenance of UFOs, and so I might give a talk about that too. I don't think I've given that talk at Science Sunday. I gave a talk about UFOs in another forum a couple years ago. Anyway, questions and comments about any of the material today? Yep.
Here we go.
With the billions of stars in our galaxy and the billions of galaxies out there, to me, it's inconceivable that there's got to be life out there.
Yeah, probably at the very least, microbial life. And this, maybe I should use the word plausibly rather than probably, because we cannot yet affix a probability to it, but we can say that it seems plausible given what we know. So we don't yet know enough to make a probability estimate, but we can certainly make a plausibility argument for it.
The closest star is what?
4 light years or so.
4 light years? Okay.
Yeah.
So any signal that we sent out hasn't gotten to that star yet.
Yeah, so
and conversely, the same thing.
Back in the 60s, Frank Drake used that Arecibo telescope to send a message like, "Hey, we're here." Some people have criticized that, like, "Oh, do you have gold?" Right? You're made of meat. That's interesting. So some people have criticized the fact that they sent out this signal, but one of the other interesting things is what they sent this signal to a globular cluster, a beehive, a thick cluster of stars that orbits around our galaxy. And most of the stars in those kinds of clusters don't have the proper chemistry for life-bearing planets to have arisen. So, but yeah, good question. Nobody knows. Other questions, comments, speculations?
We could do like a fast poll of how many people think that there is microbial life somewhere in the cosmos,
Besides here, yeah.
right?
Yeah.
Besides here. And how many people feel like there's maybe multicellular life in other,
In our galaxy. Let's limit it to our galaxy.
okay.
We're not likely to ever communicate or go to another galaxy.
And beyond that,
Intelligent.
well, yeah, okay, intelligent life?
Right. Is there intelligent life on this planet was the question.
Bob, the softballs, you swing for the fence.
About half of it, yeah. Okay.
And ones that can have technological advancements, build cars or vehicles or
Rockets. Yeah.
rockets. How many people feel that's true in our galaxy? In our galaxy.
I just don't feel confident to make my own
Yeah.
guess about that.
You can see it. It's an interesting proposal. And I think the value of Drake's equation is that it doesn't answer it, but it gives you points to think about, to
Right.
consider. What can scientists do to help try to resolve some of this, bring the percentages more in a range of not 0 to 100%, but something else. Great. Okay.
All right. I think we're kind of running over time, so one last.
Quick question. Has refined plate tectonics on Mars, has that been confirmed?
Plate tectonics like our no. I believe some of the outer moons show evidence of cracking ice and ice movements, ice flows and whatnot. Pluto and some of the outer moons, but not the bulk movement of silicate crusts, as far as I know.
There's some on the moons of Saturn. That,
Okay.
That have some.
Oh, right, the volcano there on Callisto and whatnot. So, yeah, I think that's due to more tidal action than tectonic action, the flexing of the crust of that planet. All right, thank you all.
Thank you. January 5th. Hope you have a wonderful holiday season, and we'll start the 2025 version of Science Sunday, January 5th. If you want to get on the email list, if you haven't, give me your email address as well.